Let us check what you remember from our previous discussion. We introduced last time laws, Faraday's and Lenz's laws. Any comments on them? How we formulate Faraday's law? What is the origin of induced electromotive force?
So,
magnetic field flux. So, induced electromotive force is defined by the technically first derivative rate of change over time for magnetic field flux. There also we have this negative sign which originates from Lenz's law. And what Lenz's law tells us? That the
area, but opposite the original direction.
well, it opposes always of induced electromotive force. And as a consequence, the induced electric current, they create magnetic field, obviously, like this induced electric current creates magnetic field, which opposes the reason for its creation, for the change of magnetic field flux. Depending what actually is happening, it could be if, for instance, the reason for the induced electromotive force is increase of magnetic field flux, then the magnetic field created by induced current will decrease magnetic field flux in order to oppose its original increase. And that will define the orientation of induced current and also polarity of induced electromotive force. So this is critical to mention, and that's why we have this negative sign in the equation for induced electromotive force. So, what are the areas for possible applications of Faraday's law? And in general, this effect of induced electromotive force application. Transformers, circuit breakers, like some differential circuit breakers, they are working in this principle. Also, electric generators, which we will consider in more details a bit later. So there are plenty of applications, and in order to understand more about this induced electromotive force, and today we will introduce concept of induced electric field, not only electromotive force. We need to dig deeper in terms of understanding how it's formed and what kind of properties this induced electric field possesses with respect to regular electrostatic field. So there are some differences, and we definitely need to highlight. So electrostatic field. The source for electrostatic field is electric charge. So we have stationary or mobile electric charge that works as a source of electrostatic field. However, induced electric field, so keep in mind that we were talking previously that induced electromotive force is a result of change of magnetic field flux. However, electric field exists without any test charges. That means we don't need to have any closed loop, like some while loop, in order to actually deal with induced electromotive force. We can operate in free space if we have a time-dependent magnetic field, then this time-dependent magnetic field will induce this electric field, so-called induced electric field. And let us consider such case. For instance, we have magnetic field vector which goes into the plane of the figure, and let us consider some closed loop. So if this magnetic field is a function of time, so it changes, then it will create some induced electric field. Induced electric field, we will show a bit later, is actually conservative electric field as opposite to electrostatic field. So we mentioned that electrostatic field is conservative field. However, induced electric field is different. So induced electric field vector will be always tangential to this closed loop. Delays in response. And if we consider electromotive force induced by changing magnetic field, we can recall the previous discussion. That's Faraday's law, change of magnetic field flux over time with negative sign. So now let us consider what will be the work done by this induced electric field if, for instance, some test charge Q will go around all this loop. So if there within this loop we have electromotive force epsilon, then work done by moving test charge Q within this loop like 360 degrees will be equal to Q times what? Yes, the electromotive force. So this is for work. I don't know why it doesn't work properly. Then this could be represented in another form. If we're talking about electric field, which is always like this induced electric field, which is always tangential to the circular loop, we can represent this work in terms of force, electric force acting on test charge times displacement. So what will be electric force? Q times electric field induced, like magnitude of electric induced electric field. And what will be the displacement in this case? If this is some radius r, this is the circumference of this circle. So it will be 2 pi times r. So that also work represented represent work done by electric field by moving test electric charge around this loop. So we can write that Q times epsilon is equal to Q times E times 2 pi R. From here, we express the magnitude of the induced electric field. So E is equal to electromotive force divided by 2 pi R. So this is the magnitude of induced electromotive force. And now we induced electric field, not electromotive force. And now let us check what we can substitute here instead of electromotive force, expression from the Faraday's law. What will be the magnetic field flux, FB? Since magnetic field vector is perpendicular to this circular loop, we can write that it will be equal to pi times r square times b, just area times magnetic field. So now we need to get the expression for electromotive force. That will be minus df b over t, so we dt, so we have first derivative over time, and that is pi times r square minus, I forgot, dB over dt. First derivative of magnetic field over time. Now we can substitute it in the expression for electromotive force here for induced electric field, and express that induced electric field is equal to 1 over 2 pi times r. Here will be negative sign, we need to remember. Then we have pi times r square dB over dt. And here we cancel this pi, cancel this second power and this r. We get negative r over 2. First derivative times first derivative of magnetic field over time. So this is the relationship between induced electric field and time-dependent magnetic field. So that any change of magnetic field creates induced electric field, and that is the origin of the electromotive force, which we discussed last time in the scope of Faraday's law, so induced electromotive force. So that's why we can decouple some conductor and magnetic field flux, because we can consider just empty space, and if in empty space we have any time varying magnetic field, we already automatically deal with induced electric field. So if we place there in this space some electric wire, some current, create some current loop, then of course we deal with electromotive force, and also we deal with induced electromotive force and induced electric current. However, even in free space, changing, varying in time magnetic field always induces this electric field. Induced electric field is different from electrostatic field. And what we can write here, that in general case, if electric field is dependent on position, so we don't deal with uniform electric field, and it could be any type of closed loop which we consider, not just a circle. So in this case, we want to write in general case that electromotive force will be equal to line integral over closed loop for the scalar product of electric field vector times ds, scalar product electric field vector and ds vector. So in this case, we can write, when we deal with induced electric field, that integral for like closed loop of induced electric field vector scalar product ds vector will be equal to negative of first derivative over magnetic field flux, because that stands for Faraday's law. So it will be, we can write that electromotive force is equal to this integral, and it is equal to negative first derivative of magnetic field flux over time. So this is the sign that induced electric field is not a conservative field. Because if you recall our previous discussions, we had an expression that for electrostatic field, which is conservative, integral, like linear integral over closed loop for E vector scalar product ds vector was equal to 0. So in this case, when we deal with induced electric field, this integral is equal to the rate of changing of magnetic field flux, indicating that induced and electrostatic fields have different physical nature in terms of their origin. So first, electrostatic field is created just by charges. However, induced field is created by changing magnetic field. And we have found the relationship which given by this equation. Induced magnitude of induced electric field is defined by the rate of changing of magnetic field. So now let us consider some example when we determine magnitude of induced electric field when we have a solenoid. So you remember what solenoid, some special configuration of electric current. We managed to run some time-dependent electric current through this solenoid, so it will change in magnitude over time. And that, of course, will result in time-dependent magnetic field flux, because time-dependent electric current results in time-dependent magnetic field, then we have time-dependent magnetic flux. If we have this time-dependent magnetic field, we already know that we will inevitably create some induced electric field in the environment surrounding this solenoid. So our goal is to determine how its magnitude will change as we increase distance from solenoid under two conditions. First, we will consider external space, like outside the solenoid, and also how induced electric field changes inside solenoid. So this is our solenoid with, let's say, capital N turns. The radius of the coils denoted as capital R. So now let us consider what will be the magnitude of induced electric field at the distance r from the center of solenoid if we consider this time-dependent electric current flowing through the solenoid. So let us assume that R is larger than capital R, means we are dealing with space outside the solenoid, the internal part of the solenoid, and we can write that in negative dFB over dt will be equal to negative d over dt, and here will be b times pi r squared. So that is our magnetic field flux Fp. So that is magnitude of magnetic field inside solenoid times the cross-section area of the solenoid, like this cross-section area. We don't consider anything contributing to magnetic field flux outside the solenoid, and the reason for that we already discussed it. We assume that magnetic field is much weaker outside solenoid than inside, so that's why we consider only internal flux from the through the internal cross section of the internal area of the solenoid. So now what is magnetic field? Because that is a function of time. Who recalls what will be the expression for magnetic field in solenoid if we have, for instance, here is length of the solenoid, so there is density of these coils per unit length, capital N divided by L. So that was mu naught, assuming that we have free space inside the solenoid, times small n, which is density of coils per unit length, times electric current, which flows through the solenoid. So this is our electric current. And in this case, since we deal with time-dependent magnetic field, we reach this condition for variable magnetic field over time by running time-dependent current through this solenoid. So that's why it will be mu naught times small n times I maximum times cosine omega t. So we have some time-dependent current which flows through this solenoid. So now let us determine the first derivative of magnetic field flux over time. So minus dFB over dt is equal to minus pi times capital R square times first derivative of electric magnetic field inside the solenoid. So that is mu naught times n times I maximum times d cosinus omega t over dt. Didn't forget anything. Minus pi r square mu naught n, and instead of I, we substitute time dependence of current. Okay, so now what will be the derivative of this cosinus omega t over dt? Minus omega times sinus omega t. So minus and minus, they will cancel out. So we get pi r square. Then we get mu naught times n times omega I maximum sinus omega t. Pi r square mu naught times n times omega I maximum sinus omega t. Okay, now let us consider what will be the integral over closed loop of induced electric field dot product ds vector. And that will be electric field times 2 pi r. We already discussed it. So that will be equal to minus d f b over dt. And we already have found it. So this is pi capital R square mu naught times n omega I maximum sinus omega t. And now we can express the magnitude of induced electric field as a function of this distance r, assuming that r is larger than radius. That will be equal, we cancel out here this pi, and we get r square mu naught times n times omega times I maximum times sinus omega t divided by 2r. So here we see that induced electric field will be also time dependent, because if it created by time dependent magnetic field, this rate of changing of magnetic field is different at every moment of time. So that results in time dependent induced electric field. But as we go further from the solenoid, the magnitude of electric field, induced electric field, is proportional to 1 over r, assuming that r is larger than the radius of the cross section of the solenoid. So now let us consider the option when we are dealing with a space inside solenoid. So when r is smaller than capital R, so in that case we are staying in the internal space of the solenoid. So what we also need to consider the first derivative of magnetic field flux, what we did previously. So first derivative of magnetic field flux over time will be equal. And now we need to think what we should consider. So let's say we have, let's draw, this is the cross section of the solenoid. And this is the radius of the solenoid R. And we deal with distance from the center R, which is smaller than capital R. So in that case, we need to consider magnetic field flux through this area of the circle of smaller radius, which is embedded into the internal volume of the solenoid. So that's why we consider magnetic field flux as 2 pi times small r. Sorry, not, we need area, pi times r small square times b. So instead of previous case when we considered here total area of the cross section of solenoid, and here we have capital R, here when we deal with small r, because small r is smaller than the capital R. And B magnitude of magnetic field remains the same because we have shown previously we get uniform magnetic field inside the cross section of the solenoid. It doesn't change from the center to the outer parts of the cross section of solenoid. And this will be equal to minus pi times r squared dB over dt. So let us substitute here again our expression for time-dependent electric current. dFB over dt will be equal to minus pi r square mu naught times n I maximum d over dt cosine omega t. And that will be equal to pi r square mu naught times n I maximum times omega sinus omega t. And again, this integral over linear integral over closed loop for induced electric field vector dot product ds vector will be equal to magnitude of electric field times induced electric field times 2 pi r, assuming that r is smaller than the radius of the solenoid, cross-sectional solenoid. That will be equal to pi r squared mu naught times n times I maximum omega sinus omega t. And finally, we have expression for induced electric field inside the internal volume of the solenoid will be mu naught times n I maximum, because we cancel this pi, cancel this r and this second power. So I maximum times omega over 2 here we have R times sinus omega t. And here we see for this expression for induced electric field inside the solenoid that electric field, maybe like this, induced electric field is proportional, linearly proportional to the distance. So we have increase of the induced electric field as we go from the center of solenoid to its like, let's call it surface here, external surface. And then when we go outside the solenoid, the induced electric field magnitude is reducing proportional to 1 over r. So here is important to underline that we have a solenoid with two terminals, run time-dependent electric current, create time-dependent magnetic field, which automatically is the origin of time-dependent induced electric field. And as the magnitude of this induced electric field will be defined by position with respect to the solenoid. So if we are dealing in the space inside solenoid, it increases linearly from the center to the outer side of the solenoid. If we go further from solenoid, it's proportional to 1 over r. But close to the solenoid, you definitely can identify this time varying induced electric field and actually can use it so you can transfer certain signals or use it for measuring purpose or use it for convert like transferring energy, but you definitely can um, utilize this induced electric field in certain way. So summarizing our discussion for today, we continued to look at the Faraday's law from a different angle a bit and highlighted that it's not always necessary to have closed wire loop in order to deal with induced electromotive force, specifically because of time-dependent magnetic field flux. It is possible to look at this phenomena without introducing any current loops. We may have just in the free space time-dependent magnetic field, and we have shown the relationship between induced magnitude of induced electric field and time-dependent magnetic field. There is a simple relationship between them. In any case, when we have time-dependent varying magnetic field over time, it will create induced electric field. And once we already put some current loop, create some current loop with placing a closed wire loop inside this environment where we have time-dependent magnetic field, then induced electric field will result in certain electromotive force depending on which wire loop we choose. And depending on the resistance of this wire loop, it will result in certain induced current within this loop. However, looking like from most general point of view, we don't need anything, just free space and time dependent magnetic field that results in induced electric. Induced electric field is not a conservative field because linear integral over closed loop of the scalar product induced electric field vector and displacement vector will result in the negative of first derivative of magnetic field flux over time, which is different from classical electrostatic field, which we considered previously, because this integral is equal to 0. So we consider the relationship between induced electric field and changing, varying in time magnetic field in order to determine how magnitude of induced electric field will change as a function of distance from a solenoid through which we run a time variable electric current. If this is time variable electric current, it creates time variable magnetic field, and automatically this solenoid becomes a source of induced electric field. So just to highlight here, if we run a DC current, like just let's say time independent current, so in the same direction and constant in magnitude, because DC may be it's the same direction but also time dependent, but we have in the same direction and is the same magnitude. Then magnetic field, which is created by this solenoid, will be constant. Its first derivative over time will be equal to 0, and such solenoid will not serve as a source of induced electric field. However, if this current is a function of time, it will be time-dependent magnetic field, and this solenoid automatically becomes a source of induced electric field. So we consider the specific case when the current is a function of time, and determine the equations, derived equations, which allow us to determine the magnitude of induced electric field as a distance from solenoid to outer space or position within the internal volume of the solenoid. So from the center of solenoid to its external surface. And we have shown that induced magnitude of induced electric field increases linearly within the internal volume of the solenoid as we go from the center to external surface. And as we go away from solenoid to the external space, it's proportional to 1 over r. Okay, at this point, I think we can